Swayam Prabha. Digital India. Educated India.
It is my privilege to introduce a distinguished scholar in the world of theoretical physics, the Richard Feynman of India, Professor V. Balkrishnan. A former professor at IIT Madras, where we are now seated, he is widely respected for his pioneering work in areas such as particle physics and quantum mechanics. Professor Balkrishnan is not only an exceptional researcher, but also an inspiring educator, known for his clarity of thought and his ability to make complex ideas accessible. His lectures and writings have guided generations of students and researchers, fostering a deeper appreciation for the elegance and rigor of physics. Apart from his teaching, Professor Balkrishnan has contributed a number of book reviews and science articles to the Resonance Journal of Science Education. His contributions have been recognized with numerous honors, including the prestigious Shanti Swarup Bhatnagar Prize, one of India's highest accolades in science. Through his work, he has continually pushed the boundaries of knowledge, embodying the spirit of inquiry that lies at the heart of scientific discovery. As the chairperson of RSIC, he is a central figure in defining the direction and objectives of this program and setting the standards of excellence which will motivate us for the next 6 weeks. Today, we are truly honored to have with us a thinker, teacher, and pioneer, Professor V. Balkrishnan.
Actually, you can see stars, the further stars. The universe is 13.8 billion light years old, 13.8 billion years old, but the furthest stars are actually about 42 or 43 billion light years away from us. Why do you think that happened? Pardon me? Star formation took place surprisingly close to the origin of the Big Bang. Why is it that although 13.6 or 13.8 whatever billion years have elapsed, the furthest you could have traveled, light could have traveled faster than anything else, only 13.7 billion light years away. The universe is expanding, and it's exactly, that's exactly the point. I'm not going to go into details of how we measure it or how we make this estimate. The fact is that the universe is expanding at a rate faster than the speed of light in vacuum. Because it's just like stretching a space-time fabric. It's not any material object which is traveling faster than light. That's not happening. Okay? So that makes a difference of a factor of 3. But we'll forget about that. So the distance we can think of is about 10 to the 26 meters or so. That's the longest length. So let me call the length of the universe, radius of the universe. What's the smallest length we can actually see with our eyes? What's the smallest distance we can resolve with our eyes? Can we see a micron? Can we see a millimeter? Can we see a tenth of a millimeter? Well, if you can see a fine human hair, it's about a tenth of a millimeter, right? So that's about 10 to the minus 4 meters. So we have 10 to the minus 4 meters on one side, whereas nature itself goes up to 10 to the minus 35 meters. Okay. And what's the longest distance you can see without any aid? To see stars a billion light years away, you need telescopes. But now if you have a bare eyes, how far can you see? How far can you see and estimate the distance? That's important. Because we can look at the sky and see planets and stars, we don't know how to tell the difference between them. We can't tell how far what is or anything like that. So what's the furthest that we can estimate distances? How far can you see on a clear day from the top of a mountain? Yeah, how far do you think you can see? You should be able to estimate the distance, not from prior knowledge, but you should be able to estimate the distance. You can see a distant hilltop, 10 kilometers maximum. In Chennai, on a busy day in the middle of Mount Road, you can see 10 meters, but that's a different matter altogether. Okay? You can see about 10 kilometers, 10 to the 4 meters. So you start with 10 to the minus 4 meters and you go up to 10 to the plus 4 meters. How many orders of magnitude is that? 8 orders. And what does nature present us with? At least 60 orders of magnitude, probably much more. Okay. What about time? What's the shortest length interval that you can measure? In subnuclear physics and strong interactions, you can measure indirectly timescales of the order of 10 to the minus 23 seconds. Electromagnetic interactions timescale characteristic is about 10 to the minus 15 seconds. Okay. Radioactive decay goes on for many, many years also possibly. But the shortest time scale we can have access to is about 10 to the minus 23 seconds. But there is a time scale called the Planck time, which I'll come to, which is much smaller. It's 10 to the minus 43 seconds. So you have Planck time. And what's the maximum time we can consider? We have some knowledge about the age of the universe, right? What is it in seconds? What's the age of the universe in seconds? How many seconds are there in a year? 10 to the 5 of the order of magnitude, right? And you multiply that by 10 billion. So that's the longest time scale we can think of. 10 to the 17 seconds. The age of the universe is about 10 to the 17 seconds. Again, what's the order of magnitude addition? 60 orders of magnitude. What's the smallest time scale you can distinguish without equipment, without calculation, without observation? How about your pulse? Slightly smaller than a second. Can we think of any other smaller without any equipment? How about a blink of an eye? How long does it take you to blink your eye? In normal conditions, how long does a blink of an eye take? About a tenth of a second. 10 to the minus 1 seconds. You can't tell the difference between a millisecond and a microsecond. You can tell the difference between 10 to the minus 1 seconds and 10 seconds. So about 10 to the minus 1 second. What's the longest time that you can think of? Without observation, without anything else, no aid, no telescope, no microscopes, nothing. You're put inside a room with no sensory inputs, with uniform lighting, so you don't know if it's night or day. You're given food through an entrance in which the food tastes exactly the same for every meal, so you can't tell the difference, whether it's night or day. It's like hostel food. And then no newspaper, no communication with the outside world and so on. People have done this experiment and they are asked to go and ring a bell on the wall, press a button on the wall after every hour is over, as they think. Gradually what happens is within a day or two, their time scale gets knocked out and the day extends. So they gradually go to a stage where they're ringing the bell every 2 hours and they assume it's an hour. And people have stayed there for a couple of months at a time and so on. Your time scale sense is completely screwed up. Your bodily cycles also get synchronized with that screwed up time completely. And this can last for a month or two. So I think the maximum you can tell, and whether a year has elapsed or 10 years have elapsed, you can't tell. But you can tell if a month has elapsed or 2 months have elapsed. Okay? So about a month. As a day has 84,600 seconds, you multiply by 30, that's the maximum you can tell. So that again is just a few orders of magnitude, whereas this year is about 60 orders of magnitude. Enormous. 10 to the minus 43 to 10 to the plus 17. So what we have is a window into nature, which is extremely small, decided by what? What decided that we can tell the difference between a mass of a kilogram and a mass of a gram, but not a kilogram and a microgram, but not a microgram and a picogram? What decided this? What do you think decided this? We have not evolved here to understand the universe. We evolved to survive. So it was purely survival that dictated what you could measure and what you couldn't measure. For instance, take your eyes. What is the range of frequencies or wavelengths for which your eyes are sensitive? 400 nanometers on one side and about 1000 nanometers on the other side, right? That's all you can see. You can't see in the ultraviolet, you can't see in the infrared, you can't see in the microwave, you can't see in the radio region, gamma ray region, X-ray region. You can't see at all. Why is that so? You got the bare minimum that you can see for survival. We are not nocturnal animals, we are daytime animals. You need to be able to see in the daytime. And what's the color of the sun? Basically, it's emitting in yellow, orange yellow, right? So your eyes are sharpest at that frequency. Visual acuity is maximum at the orange, red, yellow border because the sun is predominantly that color. And we don't need the information based on infrared sight and ultraviolet sight unless you have special purposes like military vision or something like that. So again, we evolved for survival. What our senses evolved for survival, which is a small bit of the full nature, tapestry of nature. So we understand a small window in mass, length and time and other physical parameters of what nature presents us with. The rest we explore with our mathematics, with our theories, with our instruments, with our equipment and so on. Okay? So that's the first thing you have to appreciate about physics, that our natural aptitude or natural skills are a very bounded set, and what nature presents us is with much bigger. You should therefore not be surprised if the laws that apply in this small window of middle dimensions don't necessarily apply to the rest of the universe, rest of the scale of range of parameters. You should therefore not be surprised that electrons can be in two places at the same time, or that the uncertainty principle tells you, puts bounds on what you can measure and what you can't. The very small and the very large are out of our scope. And the laws that apply there may be very different. Although this effect may not be visible on the Earth, the gravitational field of the Earth is pretty small compared to the masses out there, compared to the fields out there. The fact is that light gets bent by gravity. The rate at which time passes gets bent by gravity, gets distorted by gravity. And these effects play a role in the universe. They may not be apparent to us immediately. Here too, even on Earth, the gravity is pretty weak. Doesn't feel so weak when you fall down the steps. That's certainly true, but it's extremely weak. To give you a proof, there's another interaction which is much, much stronger than gravity, which controls our daily lives. Which one is that? Electromagnetic interactions, right? How do I prove that? How do I know that? Here's a simple experiment. Take a small bar magnet and bring it to on top of a pin on the table. The pin jumps up and sticks to the magnet. That little magnet, by electromagnetic force, has outpulled the entire Earth's gravity. So you see the mass, what a difference in scale that is. The force of gravity occurs on that pin is due to every part of the Earth, the entire Earth's mass. But this little magnet is able to outpull it immediately. Okay? Gravity is much weaker spontaneously, unless the mass becomes extremely large. Then it's a different story altogether. The mass has to be extremely large for gravitational effects to really start taking effect. Okay? So now let's get to quantitative stuff. We'll try to do something quantitatively. We want to know what are the parameters that control the laws of nature. What are the parameters that appear? So I want you to tell me what are the so-called constants of nature. How many constants can you think of? Let's write them all down and see what we get. Okay, what are the constants you can think of that you've come across in your physics courses? Pardon me? Gravitational constant. Okay, that's very good. It's a good beginning. Newton's constant of gravitation. How big is this? How big is this, by the way? In standard international unit, 10 to the minus 11. In standard international units, of the order of 10 to the minus 11. Okay. What else? What are the constants? Speed of light? That depends on the medium. In speed of light in free space. What constant? Say that again. Coulombic constant? Which one? Oh, you're talking about the permittivity and permeability of the vacuum. Those come about because of the choice of units that you have. They're not fundamental in that sense. Planck's constant. The mu naught and epsilon naught come about because you're using a particular system of units. You can choose a system of units where they go away. They do play a role. Mu naught epsilon naught is 1 over c squared. So it's already included here. H cross stands for h over 2 pi, which is the way we should have defined Planck's constant to start with. But unfortunately, for historical reasons, it got defined without the 2 pi, so now we put it back and call it h cross. What's this of the order of magnitude? 10 to the minus 34. What 10 to the, with the 2 pi in the bottom. Otherwise, it's 6 times 10 to the minus 34, but I get rid of that 6 with this. How big is this? 10 power 8 per second, 3 times 10 to the power 8. This is 10 to the minus 11. That's 10 to the minus 34. Order of magnitude. What else? How about Boltzmann's constant? How about the solar constant? Have you heard of the solar constant? It's some number. It tells you the mean amount of radiation that you have per unit area, per unit time, etc. But it's very restricted. It's specific to the star and the Earth. So it's not really a constant. You go to another planet, you get another sun. It's a parameter, but it's not a constant of fundamental constant of nature. What else can you think of? How about the refractive index of glass? That depends on the type of glass. So it's really not constant. That's very true. What else can you? How about speed of sound in air? It depends on the humidity, the temperature, the pressure, and so on. Not constant. Yes. How about the mass of the electron? That's constant. All electrons in the universe are exactly the same. So. How about the mass of the proton? That's constant too. But the proton is not an elementary particle. It's made of quarks. So it's a composite object. Not fundamental in that sense. Not as fundamental as I'd like it to be. Neutron, the same problem. Nuclei, the same problem. Okay. What other constants can I think of? How about the charge of the electron? Right? Charge of the electron is certainly a constant of nature. Yeah? Avogadro's number. Now that depends on, first of all, it's an ideal gas. Then it's under standard temperature and pressure. So you specified arbitrary temperature, arbitrary pressure, and said this is the total number of molecules on the average in that. So it's not all that fundamental. Boltzmann's constant is more fundamental. Well, if I multiply Boltzmann's constant by Avogadro's number, I get the gas constant. So it's not fundamental in that sense. Well, what about masses of other elementary particles? What about the neutrino mass? What about the muon mass? All these are fundamental constants, right? So, a lot of them. There's something very fundamental about these three that are not reflected in these. So when I say truly fundamental constants of nature, the primitive constants of nature, I want something that's a property of the universe and not the property of any particular object. This is a particular object, electrons, but there are other elementary particles. This is a particular charge on the electron, but there are other such particles. There are particles even with fractional charge like quarks. So this is not as fundamental. They are properties of specific objects in the universe. But these guys are different altogether. This occurs not so much as the speed of light in vacuum, not the speed of any particular object in vacuum. That's not the important part about C, but as a fundamental limit on the velocity in this universe due to special relativity. It's a restriction. It's a bounding velocity. No object can travel at the speed of light other than a massless object like a photon. And none can travel faster. So it's a restriction on the universe. That's the way we've been presented in this universe. But this is still a constant. The fact that it's faster doesn't matter. That's the stretch of the universe which you cannot measure with a ruler because the ruler is expanding at the same time. Okay? So this is truly a bounding velocity in any given frame of reference. So the laws of addition of velocities itself change by special relativity once you hit speeds comparable to c. So this is something which says the presence of c says the universe is relativistic in nature, no matter what's in that universe. What does H say? This is the quantum constant. So it's telling you that the universe is quantum mechanical in nature. You may not see it, you may not see it immediately, but it's quantum mechanical in nature. And the uncertainty principle relates to H cross to that uncertainty, the product of uncertainties in canonical variables. So this says the universe is relativistic because there is a bounding velocity. The universe is quantum mechanical because of a non-zero Planck's constant. If Planck's constant was set equal to 0 and the speed of light was set equal to infinity, you would be back in the Newtonian universe. So this is the quantum nature of the universe. This is the relativistic nature of the universe. What does this signify? After all, you can say it's a little bit like electric charge because G m1 m2 over r squared, the gravitational force, and this is q1 q2 over 4 pi epsilon naught r squared for the Coulomb force, right? But this is somehow more fundamental. Why do I say that? Because gravitation is not a true interaction. As Einstein pointed out in general relativity, gravitation is caused by the curvature of space-time. Matter causes space to curve, and the curvature causes matter to move in a gravitational field. So as John Wheeler put it, matter tells space how to curve, and space tells matter how to move. Okay? So this is entirely due to the fact that gravitation is not like any of the other forces. It is in fact it's a distortion of space-time itself. And space-time is the arena in which the drama of life happens, the drama of physics takes place. Okay? And here the arena itself, the stage itself is shifting, is dynamic. Okay? So this controls the large-scale structure of the universe because at small distances, gravity is pretty straightforward and trivial. It's like Coulomb charges. But once you go to the scale of the universe, it's a different matter altogether. The large-scale structure of the universe is decided by capital G. The relativistic nature of the universe is decided by the existence of small c, and Planck's constant decides the quantum nature of the universe. Okay? They are the true constants of nature. But unfortunately, or fortunately for us, they don't come in neat packages of length, mass, and time. But we can convert it to that. We can do that very straightforwardly. Let's write down the dimensionalities of these quantities. We start with Newton's law between two particles, G. And we write down the physical dimensions of each side. What are the physical dimensions of F? Mass times acceleration. So what are the physical dimensions? Sorry, LT to the minus. The dimensions of G multiplied by, this is m squared. Agreed? So the dimensionality of G is kilogram inverse length meter cube second to the minus 2. What are the physical dimensions of C? What are the physical dimensions of H cross? Energy multiplied by time. So given these three constants, capital G, C and H cross, can I find a quantity of dimensions mass? How do I do it? Have you studied dimensional analysis already? Like you find the time period of a simple pendulum with dimensional analysis, proportional to square root of L over G and so on. Same trick. What would you do here? Yeah, so what I'm going to do is to say M Planck. I'll call it M Planck. No, C, I want C here. No, this is an M equal to, and I put these power, raise these two powers alpha, beta, gamma, and then you end up with three simultaneous equations for three constants, alpha, three variables, alpha, beta, and gamma. You do the same thing for time Planck and length Planck. You get three equations, three unknowns. You solve it and you get what the length, Planck, mass, time, and length are. Do I have to do that or will you do that? Do you know what to do? Yes? Equate powers of m, powers of l, powers of tm. And then you end up with the following answers. I'm not able to write this. So these are the three dimensionless combinations that you get out of time Planck, length, mass Planck, and length Planck. These are the true constants of m, l, and t in nature. Because we didn't get length, mass, and time directly, but we got indirectly capital G, H, and C, and from that we constructed length and mass and time. And you put in numerical values, this is of the order of 10 to the minus 35 meters, this is of the order of 10 to the minus 43 seconds, This is of the order of 10 to the minus 8 kg. This is the lowest length you can think of. This is the lowest time interval you can think of. This is not the lowest mass you can think of. It's pretty large. 10 to the minus 8 kilograms is pretty large. 10 to the minus 5 grams. So almost within lifting weight. So this has a different role than these two guys. Okay. This is already about 18 orders of magnitude less than what we can directly measure. This is already 20 orders of magnitude smaller than what we can measure. This is very large compared to elementary particle masses. The mass of an electron is 10 to the minus 30 kilograms. The mass of a proton is 10 to the minus 27 kilograms. This is 10 to the minus 8. So this has a different interpretation than these two, and I'll come to that in a minute. Okay. You could ask, what happens at this scale? What happens at these length scales and time scales? You would have read popular books on the Big Bang theory. You have heard that the first 10 to the minus 43 seconds is a mystery. We don't know what happened, and after that we can tell you pretty accurately what happened. The reason is this, that Planck time combines relativity, gravitation, and quantum mechanics. And on this time scale and this length scale, space-time itself undergoes quantum fluctuations. So it's not like a regular continuum, it's like a froth. It is constantly changing. If you dissolve some soap and stir it around inside a basin, you see the froth forming on top, and the froth continuously changes. Bubbles burst, get connected, the geometry changes all the time. So this is the length scale and mass scale on which the quantum nature of space-time becomes manifest, and you can't probe below that. The very notion of length and time lose meaning below that, this limit here. We assume space to be continuous, time to be a continuous variable. That's only valid for length scales and time scales greater than Planck length and Planck time. Below that, we need a quantum theory of gravity, which we don't have. Not a full one anyway. Now you could ask, what's the significance of this? This is not the smallest elementary particle mass. It's in fact much larger than elementary particle masses. This is that mass scale at which the limit on a mass of an elementary particle breaks. This is the largest mass an elementary particle can have. In precise terms, if I put the energy equivalent of this mass inside a volume which is a Planck length mass cube, Planck length cube, the system becomes a black hole and disappears. Okay. So you cannot have an elementary particle which is more massive than this object. Because if it occupies a volume of Planck length cube, it becomes a black hole. Now I can ask the following question. You can say, oh, so you told me that there is a fundamental length in nature below which you can't go. There is a fundamental time in nature, the time interval below which you can't go. And there is a mass scale which is above which you can't go with a single elementary particle. Okay. So you could ask, is there a dimensionless combination of these three quantities which is a special number? Some combination like this. Some combination. Pardon me? Length, mass and time. I've derived these quantities because they are more familiar to me than the C, G and H, right? And anyway, I'm saying M, L, T are fundamental quantities, physical parameters. So can I find pure number, dimensionless, like 2 pi or E or 7.1 or square root of 2, some pure number, no dimensions. Do you think I can find one like that? If I could do that, if such a number existed, it would be a very special number because it's formed out of the most fundamental constants of nature and is dimensionless. So it doesn't depend on the units you choose. Absolutely pure number. Do you think such a number exists? What's your intuition tell you? Do you think it exists? There's a special number in nature. The right hand side should be 0. The simultaneous equations. So you solve for alpha, beta, gamma, you get 3 simultaneous equations. But the right hand side must be 0 because the right hand side is a pure number. That's the set of homogeneous equations. You cannot have a non-trivial solution because the inhomogeneous ones tell you mass length and time, Planck length, Planck time, etc. Since the inhomogeneous equations have solutions which we found, the homogeneous set cannot have solutions and must accept the trivial solution. So that pure number must be m to the 0, l to the 0, t to the 0, which is 1. 1 is certainly a special number. So 0 and 1 form our number system. Okay? So there is no special number in the universe. Not even 42. Okay. This is a demonstration of that fact. But if I took a problem and wanted to solve it by dimensional analysis, this dimensional analysis is not as trivial as it made out to be. Take the length of a simple pendulum. So here's a simple pendulum moving back and forth. And I have L here and M here, the mass here. And the bob swinging back and forth. And you're told that T is square root of L by G multiplied by 2 pi. 2 pi you can't hope to get from dimensional analysis because it's a pure number, independent of units and so on. But square root of L over G you get it. How do you do this problem? Some constant into the mass of the pendulum to a power alpha, the length of the pendulum to a power beta, gravity to the power gamma, because gravity is the force on it. What else can it depend on? You've done this. Everybody has done this exercise. You get the square root of L over G, there's no dependence on M. M power turns out to be 0. This has been taught to you, right? But now I come along and I'm going to spoil this game. I'm going to tell you I don't believe this. How do you know the fundamental constants of nature don't appear here? How do you know there isn't any C to the delta, Planck's constant to the epsilon, capital G to the power eta, Boltzmann's constant to the power psi, etc. How do I know this? How do I know these don't affect the time period of the pendulum? The moment I put in a fourth parameter here, you don't have enough equations. You have an equation for the coefficient of m, power of m, power of L, power of t. And you solve the problem neatly with 3 unknowns, 3 variables. But I'm going to come and say it should depend on all this. What's to stop me from doing that? Now is where the physics comes in. Till there it was algebra, but now the physics comes in. Why do I not have C in this problem? Well, now this is physics. It's not pure mathematics. C must be eliminated on the basis of physical arguments, not mathematical arguments. Mathematically, you can't eliminate it. Everything is dependent. Why should I say that it's not reasonable to put C to the power delta here? It will not appear in this formula. Why is that? Pardon me? The ball has a? Yeah, the mass of the bob, I'm taking m to the alpha.
travel at the speed of light or travel dependency on the speed of light, the object should not have a mass.
Object can be half the speed of light. It's not at half the speed of light, it's still sizable, right? So you should have it. But you're quite right that the bob is not moving relativistically, it's moving at a speed much smaller than the speed of light. It's not relativistic, it's Newtonian. So because it is non-relativistic motion, this goes away. It's no charges, no electromagnetic forces involved, therefore this goes away again. The bob is doing classical motion, not quantum mechanical motion. So there's no Planck's constant. There's no Boltzmann's constant because there's no heat energy exchange either way. It's all at constant temperature. So Boltzmann's constant goes away. And what about G? It's already there in this. This quantity is equal to m mass of the earth. Over the radius of the earth squared, which happens to be about 9.8 meters per second on the surface of this earth. So it's already there, and therefore that goes away. Then you can make this approximation. And then you get your square root of 2 pi root square root of L by G. You get square root of L over G. If there had been another length scale in the problem, you're finished. Because if you had two lengths, when you ask now, I let this swing, and there's a free joint, so it can swing in such that these two are not in a straight line. What's the time period like? Now you're finished. You cannot do it by dimensional analysis because whatever answer you get, I can always multiply it by a function of L1 over L2, which is a dimensionless combination. And there's no way of deducing what it is from dimensional analysis. So you have to eliminate variables till you have just the right number. This, in fact, is a very hard problem. It leads to what's called chaos. It leads to extremely irregular motion. Not at all trivial. Here's another example of the same thing. A very mundane example. I have a cistern. The pipe connected to it. And there's water in the cistern. And the water flows out through this pipe. The length of this pipe is L. The inlet pressure is P inlet. The outlet pressure is P outlet. The radius of this pipe is R. So I have a constant inlet pressure, constant outlet pressure, atmospheric pressure here, and the pipe flows in streamline, just water escaping from a cistern. Let's assume steady flow, no turbulence, no irregularity, very steady flow. Streamlines are all parallel to the pipe's axis, flows out. What is the rate at which this discharge occurs? What's the volume per unit time? Given this pressure and this pressure. So the pressure head is P inlet minus P outlet into delta P. What do you think it's proportional to? Would you agree if I argue like this? I say that the broader the area of this pipe, the greater the flow. The greater the area of cross-sectional area of the pipe, the greater the flow. Right? And it's all flowing in a streamline parallel to each other. So it's proportional to the area, definitely. And it's multiplied by the average velocity of this water. Because if the velocity is v, everything in a cylinder of length v is going to fall out per unit second. So you get q. Area, let me call it A, and then the volume. Pi r squared v, where pi r squared is the cross-sectional area of this pipe, circular pipe, and v is the velocity of the water. Would you agree with this? You can test it out by experiment under carefully controlled conditions, same temperatures, constant constant pressure head, and so on, and slow streamline flow. If you do the experiment, it turns out that the Q is proportional not to R squared but R4. What physical assumption have I made which makes it R4 rather than R squared? Forget R4 for the moment, but why is it not pi R squared V? On the? Yeah, so I have a pressure head which is constant. I'm not going to say that this water which flows out. So I'm going to constant input of water into the sum so that the pressure head is constant. And the pipe is very narrow compared to the dimensions of the cistern. What assumption have I made that's wrong? Every building contractor knows this because he knows the difference between a sanction of a half-inch pipe and a 1-inch pipe. Because the factors are as r to the power 4, instead of, if you double the radius, instead of 4 times the water, you get 16 times the water. Quite handsome profit. What do you think is the wrong physical assumption here? Say that again.
Since it's dependent on area and the first equation again the V, so the constant also will increase.
Why?
Because we're making it R power 4 itself, so become pi square into R power 4.
No, this one is proportional to R. Experiment shows that it's proportional to some CR power 4. Yeah, that's not a bad assumption. Constant velocity along a streamline is not a bad assumption. On the? No, pressure is an external control that I can control. By having a big enough cistern, small enough pipe, pressure head can be made constant. Gradient of what? Yeah, there's a pressure gradient. The pressure gradient is delta P over L. That's constant. We say that again? Yeah, I have assumed the fluid is incompressible. Otherwise, the whole thing changes. Water is pretty incompressible. It's pure physics question. What have I neglected? I have assumed constant temperature on both sides, so there are no heat effects at all. But it's a very physical thing that I've forgotten about. Let me give you a hint. The fact that if I look at what the pipe is doing, this is the central axis of the pipe. So the streamlines are going like this. No vorticity, no eddies, no whirls, no so on. All streamlines are parallel to each other and parallel to the axis of the pipe. But there's one crucial difference. There's viscosity in the problem. Viscosity is the friction internally that the fluid exerts on its own elements. So where is the pipe velocity maximum? In the center. What's the velocity at the edge surface here? Theoretically zero at the edge, right? So the velocity profile actually goes like this. Greatest at the middle and smaller as you go to the edges. So this formula is correct, except that you got to write this as the average value of V, averaged over the cross section. To say how the velocity profile changes, I need hydrodynamics. But I'm sitting on a desert island with no books on hydrodynamics. What should I do next? Yes, it's got to be the average velocity. What can this average velocity depend on? It's function of the delta P over L, the viscosity of water eta, and R. So you have to do a subsidiary problem. You write the discharge rate as pi r squared times the average velocity, but the average velocity must depend only on the following physical parameters: the pressure head, the radius of the pipe, and the viscosity of water. So do a dimensional analysis to find the power by which this depends on R, and it's r squared. And you put that in here and you get your final answer, that the actual answer is equal to delta P over L times the constant. Some constant times these guys. Now I was lucky because there are two length scales in the problem. There's an R and there's an L. If I did not split up the problem in this fashion, I could have multiplied my answer by any function of R over L, which would be dimensionless, and the whole thing is gone. I got rid of that cleverly by saying that it depends only on the pressure head divided by L, the pressure gradient. So it occurs in this combination. And now the powers are easy to find. Okay. So even as mundane a problem as water pipe discharge involves some careful thinking. Alright, this talk I'd like to turn to a different subject altogether. Not so much physics as an application of a subject which is very relevant to physics. Most of our understanding of nature is statistical in nature. Probability and statistics are in this understanding. Physics or quantum physics, whether it's thermal physics or statistical physics, statistics and probability play a key role, fundamental role in the entire thing. All of you have done physics experiments or experiments in physical sciences where you are asked to do a reading, take a reading twice or thrice or 10 times and take the average and so on. And then you realize that the numbers that you get as your results are not always precisely equal to the same number, but there's a scatter above the mean. A lot of time spent in asking what the scatter is, what the error is, relative error is with respect to the mean and so on. So what I thought I'd do is to introduce to you some probability distributions, which you've already learned about, I'm sure, in school, but we'll go through it once again, just so that we have our ideas clear on this. Okay. I take a coin toss as an experiment. Coin I'll assume has a head and a tail at side, and the result of tossing it once is either a head or a tail and nothing else in between, just two values. If the coin is unbiased, the probability of getting a head or a tail is a half. If it's biased towards heads, the probability of getting a head is slightly bigger than half, and the probability of a head and equal always to 1. It's the total probability at the end of a toss. Okay. So this enormous number cancels against this exactly with the help of this. This e to this enormously small number cancels with this exactly, and you're left with some numbers which are finite numbers. And I leave you to prove that this is of the order of 0.08. So that's an 8% chance, which is pretty large compared to 10 to the minus 30. So this binomial expansion increases very sharply and decreases very rapidly. You can ask, what's the average number? What's the average number of heads that you get? In the Bernoulli trial, this stands for standard deviation. Goes like the square root of n, whereas the average value goes like np in a Bernoulli trial. And for p equal to half, it's n over 2. Okay. So much for the binomial distribution. We can deduce all its properties with no problem at all. Now I ask a different question. I give you a coin in which the probability of a head is little p and tail is little q, and I toss this coin repeatedly till I get a head and then I stop. I may get it the first time, I may get it the second time, I may get it the third time, etc. Right? So what's the probability that I get it on the nth toss? So note the experiment very carefully. I toss this coin, whose a priori probability of a head is little p. I toss it once. If it's a head, I stop. I toss it. If it's a tail, I continue. I toss it. If it's a head again, the second toss, I stop again. What's the total probability that I get a head in the nth toss? If the coin is biased, so it's a little p. Do you agree with the following statement? So let P of n be the probability of a head on the nth toss. Right? Do you agree with this? Summation n equal to 0 to infinity, P of n must be equal to 1. I may not get a head for the first 500 million tosses, I may get it in the next one. So technically I have to sum all the way to infinity. The total probability of getting a head eventually is 1. What is little p of n? It means the first n minus 1 tosses must be failures and the nth toss must be a success. What's the probability of failure in the first toss? No, little q. Little q. Right? So the first toss gives you the first toss. First toss must give you a failure. Second toss must give you a failure. It must happen n minus 1 times. The probability of that happening is q, 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 n minus 1 times. And then success. If I tell you the first time I get a head is in the nth toss, the first n minus 1 tosses must have been failures. The probability for that q to the n minus 1 times q. Is this satisfied? Sorry, this is n equal to 1. There is no such thing as a zero toss. Is this true? Take this p out and then it's a geometric series. First term is 1 and the common ratio is q. So the answer is 1 over 1 minus q multiplied by p gives you 1. Okay. What do you call this distribution? It's not binomial. This is n is a random variable here. It's not exponential. Single variable anyway. It's a very direct name. Geometric. It's a geometric series, so it's a geometric distribution. Just like that was the binomial distribution. Geometric distribution, right? Take the gas in this room and let's assume. By the way, what's the average number of tosses for which you need when you get this head for the first time? You have to multiply this by n, the weighted sum of this divided by the normalization. What would you expect it is? Show that this answer is 1 over p. So if the coin were entirely heads, completely biased towards heads, you'd get it in the first shot. If p is 0, entirely biased towards tails, you'll never get it. Right? On the other hand, if p equal to q equal to half, you get it in 2 tosses. The average value is 2, which is very physically appealing. There are many other things you can do with this geometric distribution, but let's look at a problem in continuous time, because we want to bring in time somehow to the whole thing. That's going to be my last example. And it has to do with radioactive decay. So I have a lump of material with a radioactive nucleus in it, and this nucleus decays at random times. Every time it decays, I record it on a Geiger counter. I get a click on the Geiger counter. It's a huge sample, so I can do this experiment for a long, long time. And I have this radioactive material which decays at the rate lambda. So there are lambda decays per unit time. And I can measure this lambda. It's related to the inverse of the half-life. Okay? So I have a clock. And here's time. And I start the clock off at 0. And every time there's a decay, I put a cross. And it goes on forever. So every cross is a decay event. Now I ask, what is the probability that I have exactly n decays in a time interval t? I measure it for an hour and ask, my time period is 1 hour, my time interval is 1 hour. What's the probability that I get n decays? What is the range of values that n can take? 0 to infinity. Right? How would I approach this problem? It's completely general. Right? I want the probability that I have n decays in time t. This t is fixed, some interval of time over which I do this experiment. And I want this. This is the random variable. How do I solve this problem? So I start by saying, suppose you look at one decay. Here's the system going along, and suddenly there's a click here. Nothing happens till here, and nothing happens till time t. Let's call that capital time. The cross happens somewhere here. If there were no decays in this interval, then the event would look like this. Nothing. If there were 2 decays, it would look like this. And so on. I want the probability that there are exactly n decays. It runs from 0, 1, 2, 3, etc. Let's do the 0 case first. Nothing happens. Okay. That means nothing happens in this time interval, delta t, delta t, delta t, delta t, delta t. I break it up into n pieces. Nothing happens in any one of them. What is the probability that something does happen? The probability that something happens in a time interval delta t is lambda delta t, because lambda is the average number of decays per unit time. So the probability that nothing happens is 1 minus lambda delta t. So the probability that nothing happens the entire time is. I broke up my time interval into n pieces, each of them in an infinitesimal time interval delta t. It is small enough, decay occurs. The probability that nothing happens is 1 minus lambda delta t, and the decay probability is lambda delta t. I want all these factors to be 1 minus n lambda delta t. And the answer is the limit as delta t goes to 0 of this object, subject to this constraint. So p of 0t equal to limit delta t goes to 0 or n tends to infinity. Okay, delta t goes to 0. But this is t over n. So this form 1 minus lambda t over n to the power n, and you want the limit as n goes to infinity. What's that equal to? What is limit 1 minus x over n to the power n as n tends to infinity? You must have come across this. Exactly. That's a definition of E. Put x equal to 1, you end up with 1 minus. So we have our answer. Is 3 of. E to the minus lambda t. You wait long enough, there will be a decay. The probability that nothing happens for time interval t decreases exponentially as t increases. How would you do p of 1 comma t? I leave you to do this as an exercise, because 1 comma t, you will do the following. So suppose the decay occurs here, delta t. Nothing happens for time t1. The probability of that is e to the minus lambda t1. And something happens in this interval delta t1. So the probability is lambda delta t1. Then nothing happens for the rest of the time, it is e to the minus t minus t1. And you have to integrate from 0 to t dt1. Sum over all possibilities, because this could have happened anywhere in between. And you end up with what p1 of t is. Then for P2, you assume that in time t1, one decay has occurred, then the second decay occurs at time delta t1, and then third one occurs. Nothing happens after that. So you end up with P of. It's called distribution. Reactive decay satisfies Poisson distribution. So the answer is the Poisson distribution. Occurs everywhere. But this recursive procedure will help you calculate the probabilities. What's the average number of decays in time? Well, work this out, because you've got to multiply this by t and then integrate. It should be so, because I already said that lambda is the mean rate of decay. So in time t, the number of decays on the average is lambda t. Could have written that down without a calculation. So the binomial, geometric and Poisson distributions are among very basic distributions. if another occasion arises, we'll talk about the Gaussian distribution, but I'm sure there'll be other speakers who will talk about the distribution.